Welcome back to Search in a Nutshell. So in today's video, we're going to be having a look at basic search strategies. We're going to be walking through BFS, UCS, DFS, and DFID. We're going to be talking about what is a search strategy. We're going to show examples of how the traversals look for each of the algorithms. We're then going to briefly jump across, look at essentially the theoretical guarantees of the algorithms, right? In terms of completeness, optimality, and then their worst case time and space complexity. And we're going to be describing that in terms of these common terms instead of graph theory with V and E, which you absolutely can. We're going to be describing them in terms of the branching factor B, depth D, and depth of the tree M, which is slightly different. Okay, so to get started then, what is a search strategy? Well, in the previous video, we've looked at the idea of search. We're going to be solving sequential decision-making problems by building up some form of search tree, but the trees are large and we're going to need ways to traverse the tree effectively, okay? So this is what search strategies are. This is where they come into play. We essentially need to have some form of way to order the nodes in our tree. Which of these frontier nodes, these nodes we haven't looked at yet, which seems to be the most promising direction, right? Which ones do I think will hopefully get me to the goal faster? This is the order we choose to expand nodes. We're going to have some form of, you can call it a bunch of different things, but some form of evaluation function that's going to rank each node. We'll see that algorithms like BFS and DFS are so simple that you can simply just implement this as a queue-based structure anyway, but all of the ideas kind of come together. So let's have a look then at BFS first. So BFS stands for Breadth-First Search, okay? So we are going to be essentially, in BFS, we're going to be prioritizing searching by level before we continue downwards, okay? So BFS wants to look at all possible actions I can take at this layer, generate and expand all of those nodes, and only continue down to the next depth, to the next level in our tree, if we've already exhausted the previous level. So essentially, right, it is drawing, BFS is doing this breadth-based approach. In BFS, we first, of course, expand the root node. That happens in all of these. What happens then is we generate our two children. Okay, so I'll write the number then of expansion order. It expands one first, then each of these is up to tie breaking. They both look the same, they're both depth 1, okay? Well, up to you. I'll go left first, right? So we expand this one second, we generate its children here. Ta-da! I'm drawing solid lines as actually generated, right? Whereas the dashed lines are showing what the tree might look like in the future. Dashed lines essentially mean that they don't exist yet, okay? This is just for visual demonstration. Okay, so after this, before we get to look at these nodes, BFS says, oh, but look, this thing still looks more promising up here. This is the third expansion. We generate its children, so forth. Then we would look at, again, just leftmost. Again, all of these are tie breaking, up to you. In terms of leftmost traversal, we'd expand 4. If it had children below, we would generate those children. We're saying in these examples, okay, these are dead ends or something like this, right? We've run out of options. So what we will do is we will essentially then just continue across and expand the rest of that level. BFS is, I think, extremely easy to understand and to visualize, right? Okay, so that is done. Now, let's walk to uniform cost search. So if you remember, BFS, when we go over here and jump at this, BFS is doing this lovely just by branching. It's kind of making this innate assumption, though, that these two nodes here, the 2 and the 3, well, these have the same cost, right? And that this node up here in depth 1, well, this must still be a smaller cost than these nodes below in the other subtree. Well, essentially, all of this is just to say that BFS is assuming that the world has no difference in action costs, okay? The issue here is when the costs along the edges, when the cost of your actions are not uniform, okay? So when they're different, right? When this one is a cost of 1, this is a cost of 2, and so forth, well, then the world is a different situation. And this is where BFS loses its ability to be optimal. That means this is where UCS, Uniform Cost Search, also known as the Dijkstra's algorithm, which you've probably seen in an undergrad computer science course. Well, Dijkstra/Uniform Cost Search is essentially the same strategy as BFS, but it works with non-uniform costs. So, of course, we expand the root first. We're going to generate its two children. Now, we choose to expand in UCS by G, by the cost so far, right? So not just the cost of the edge when we get down to the bottom, it's the cost of the entire path to that node. In this first case, okay, the left side tree here looks better, right? This is going to be the second node that we expand. We will generate its children, okay? And so these children are generated with a cost of 4 and a cost of 3. Now we choose based on the lowest cost so far, which we're calling G of n. Well, it actually ends up being still this node. So we go over here, we expand this, we generate its children, and now we have some interesting decisions. So we have that this was a cost of 4, this is 3, this is 3, this is 3. So we have these 3 nodes here, which essentially the tie breaking can go any way that you want. We'll just say, hey, we expand this 4. And again, these are the baselines, so they don't find anything else. So you would expand these 3 nodes before you ever go back and you expand the last node here, which had the cost of 4, which was the largest. So UCS is also extremely easy to understand. And to write up what the strategies were, well, BFS actually is this essentially first in, first out strategy. So the first things that enter the queue, well, they're the first ones out, right? So these layer 1 get expanded before everything else. Now DFS is what we're going to be calling a last in, first out queue. Okay, so the last node that was added to the list is the one we look at first. That is going to essentially mean that we're doing this depth-wise. We're going down as far deep as we can first. So UCS does this in a similar way then, as essentially the cost so far. So we're moved to a priority queue there instead of just a generic queue. Now, DFS has this idea I just wrote down of last in, first out instead of first in, first out. What that means is the very last thing we've added is the first one we expand. This essentially leads us into this downwards behavior, right? So DFS tries to go all the way down as deep as it can before it essentially backtracks to come back up. So let's have a look at that. So of course, we expand the root node. Now, DFS also, you can do it different ways. Generically, sure, it would generate the 2 children. Traditionally, where DFS is actually still being used, and we'll show at the end that it is still useful in real problems, it's because it actually saves us on memory. So DFS is used in problems where we just don't have enough access to store the whole tree. So it has this cool thing where it can just go all the way down and then backtrack when needed and generate the other children. So I'm going to do this. It does not generate the other child here, okay? At first, it only generates 1. We expand this. We only generate 1 child again. We expand this. There was nothing there. So we backtrack up. We generate the other child that we would have needed. We expand this. Found nothing. Backtrack, backtrack. Generate the other child. And so forth. So this is DFS. DFS is extremely easy to understand as well. Okay, so let's jump over here then and then talk about the actual relative strengths and advantages. They're essentially their theoretical guarantees. BFS is complete and optimal. It is great. Now, the issue with that is this only works in worlds, and during my asterisks, it only works in worlds where, again, the depth is related to the cost. This happens when you have uniform cost actions, right? Everything moving, you can only move in 4 directions in a grid, for example, and each of those only have a 1 cost. Therefore, BFS would work. In problems that are harder, that have different costs associated with the actions you can take, say all of a sudden diagonals are cheaper than straight moves, well, BFS loses its completeness and optimality, and this is where then UCS just enters in as essentially the better version of BFS. Which one do you want to use in practice? Do you want to use BFS or do you want to use UCS? Well, if there are costs, you have to use UCS and it's the better algorithm. In the case that the costs are all exactly the same, they are uniform, you can use either, they operate exactly the same, but UCS actually is going to be maintaining an additional closed list. It's going to be detecting duplicates. Because of this, it actually does very slightly more work. So really, yeah, just if there's the same costs everywhere, just use BFS. It's actually slightly faster and more efficient. Okay, so then we have DFS. Now, DFS, interestingly, is not complete and it's not optimal. I show you this in the full video if you want to go look at that. But essentially, right, we could have this infinite tree all the way down, which means you may never terminate. There's also these other issues that you can enter into these cycles. You may never be able to escape, and then there also has all these issues with zero cost actions if that exists in your world. And then finally, right, say it goes all the way down, it finds some lower goal. Well, that's not guaranteed to be the best goal. There could have been another target higher up that was more promising. You didn't find it, right? You didn't find the best version to the goal. You went all the way down and found a version. It is not optimal. Okay, so time and space complexity, we're talking always about the worst case, right? So we want to classify in at least this aspect as opposed to practical performance. Well, how bad can our algorithms actually be? We describe this usually in our search world in terms of the branching factor B, so how many actions, right, how many things you can do at every point. The depth D of the solution, okay? So D is the depth to the solution, but we also talk about the depth M of the full tree, right? So the solution could be substantially higher than the actual bottom of the tree, which could even be unbounded, right? M could be infinite. So in terms of time and space complexity, what ends up happening is both of these are just going to be B to the D, okay? So for every layer, right, you have B decisions, and then you might have to do B decisions all the way down to the depth of the goal, so it becomes B to the D. Pretty simple. This is shared by both BFS and UCS, which kind of makes sense, right? They're very, very similar ideas. DFS is a bit different, right? Because first off, we had this idea, right, of different levels of generating children. We weren't generating all the children, we were just generating one child at a time. Now, the other aspect of this is because DFS goes all the way down, we introduce M instead of D, right? We could go all the way to the bottom of the tree. That could be unbounded, right? So that's why M could be substantially larger than D in practice. Because of the space-saving thing here, the cool thing is it's a multiplication instead of to the power. So instead of B to the M, right, it's actually BM. We're able to only store one small part of it at a time, and you might need to only store that all the way down the path. And you're able to remove and throw away things as we backtrack. However, here it is B to the M, which is substantially worse than B to the D, or could be, okay? Now, the final part of this, let's jump back and do Depth-First Iterative Deepening. You may not have heard of this one, but essentially what it's going to do is it's essentially doing a depth-first traversal, but it's borrowing the strengths of BFS, which is going to essentially correct the behavior of DFS. So it's restored completeness and optimality, and then in time and space complexity, well, what's happening is we're going to be moving away, we'll show how it works, moving away from this unbounded M back to essentially the actual depth of the solution D. So our worst case will return. Here it's the same thing, right? But instead of storing all the way down to the bottom, it's now D. Okay, so let's have a look at DFID, right? So DFID is going to be doing depth-first traversal order. We're doing these deep dives, but what's happening is we're fixing the issues of these unbounded dives all the way down because we enforce a depth limit at every iteration. So this kind of weaves in the advantages of like a BFS traversal as well. So it's a weird hybrid between the two. In the first iteration, it's completely trivial. We expand the root node just like before. The issue is that we have a depth limit of 0. So we don't generate the child below it because we say, oh, it's exceeding our depth limit. We check, have we found the goal? No. Obviously the goal is likely not at our start location. Then we continue. So in the next iteration, we do the same thing. We're going to do DFS where we generate one child at a time, right? This is the implementation hack. We check then, okay, so let's also then expand this node. This is the second node we expand. We don't generate its children, right, because they exceed our depth limit. Then we would backtrack. We go across here. We also expand this. We find nothing. The goal was not in here. Okay, so we continue on to the next iteration of the algorithm and so forth. So we will do this all the way, right, where again you do this, then you generate its child this time. This is just doing DFS again. We expand that, we find nothing, we backtrack, so forth. So the difference is, again, even if this was continuing lower, we wouldn't go lower, we wouldn't generate those children. 4, it backtracks, generates this, expands that. 5 generates this, expands that, and so forth. Okay, so DFID is essentially doing depth-first reversal with BFS built in. It actually improves upon DFS by restoring some of these ideas. Obviously, its practical performance is kind of repeating a lot of the same work, right? It's already seen this, but it does it again. So this is a bit silly. It messes its practical performance a little bit, but what's really interesting is what we're seeing is it's essentially avoiding, because of the limit, right, we're avoiding this unbounded M depth all the way down to the bottom of the tree, which could be unbounded. And this is where we're kind of returning to our B to the D and BD. So these are your basic search strategies. We call these uninformed search strategies. These are the things I think you constantly learn in your introduction to search classes. Sometimes we don't often go beyond them. So please join me in the next video when we look at the A-star algorithm, which is a state-of-the-art, extremely important algorithm in the field of AI. So please join me there when we start discussing informed heuristic search algorithms. Thanks.